Okay. Thank you. I thank the organizers for the opportunity to give this talk in this conference. It is a talk concerning a work with Luisa, and the work will appear on Statistics and Probability Letters. It's a very short paper, and I have a short outline. I discuss some preliminaries on large and moderate deviations, and I mainly refer to the book of devyations as a reference on this topic. I present the model and the results. I start with the basic definition of large deviations. It is the concept of large deviation principle, and I use this acronyms. And I present this concept by referring to family of real valued random variables, because in this talk I consider random variables taking values on the real line. So let Z T be a family of real random variables, and this family satisfies the large deviation principle with speed boot T and rate function I if I have these three conditions. Boot T is a family of numbers that goes to infinity as T goes to infinity. I is a function defined on R, taking values on 0, infinity. Infinity is allowed, and it is lower semi-continuous. This means that the level sets are closed, and I have these two bounds, the upper bound for closed sets and the lower bound for open sets. The rate function is said to be good if the level sets are compact, and this is a stronger condition. In several common situations, and in particular in our results, the rate function uniquely vanishes at some point Z0. And in such a case, we can say that the family of random variables converges to Z0 as T goes to infinity, at least in probability. This means that if Z0 does not belong to the closure of the set S, this probability goes to 0. Then, again, if this condition holds as a consequence of the definition of LDP, we can say that, roughly speaking, this probability that goes to 0 actually goes to 0 exponentially fast with respect to T, and in this way. Note that since Z0 does not belong to the disclosure, this infimum is strictly positive. Now I present the Gartner-Ellis theorem, which is the main large deviation tool used in the proof of our results. For all theta, I have to consider the limit, the pointwise limit of this scaled logarithm of moment generating functions. I have ZT, I multiply the argument of the moment generating function by T, and I divide it by T. I take the limit. This limit can be equal to infinity for some point, but for theta equal to 0 is equal to 0, because I have this quantity is constant when theta is equal to 0, and I can consider the domain of the function lambda defined in this way, and okay. Moreover, I can consider the function lambda star, which is the Lagrangian transform of lambda defined in this way. Then, if lambda is essentially smooth and lower semi-continuous, the family of random variables satisfies the large deviation principle with good rate function lambda star. I also recall that this function is convex, and also this function is convex. Probably it is not it's not so common, this definition, so I present the definition of essential smooth function in the next slide. This is a reference. The interior of the interior of the domain of lambda is non-empty. I recall that I have this condition that theta belongs to the interior of the domain of lambda. Moreover, the function lambda is differentiable in the interior of the domain of lambda. And finally, the function lambda is steep. This means that if I have a boundary point of the domain of lambda, finite boundary point, for every sequence theta n of points in the interior of the domain of lambda, which converge to the boundary point, the absolute value of the derivatives of the function lambda in these points tends to infinity. Okay. As a particular case, if the function lambda is finite everywhere and moreover is differentiable everywhere, this condition holds true because this final condition holds vacuously. Okay. Now, I want to discuss the concept of moderate deviations. This term is used in the literature to introduce a class of large deviation principle, which depends on a class of positive scaling AT. This class of large deviation principle fill the gap between two asymptotic regimes. Here my presentation concerns the case on R for simplicity. The two regimes concern a convergence in probability to a constant x naught and the rate function with some speed Vt and with a rate function ILD, which uniquely vanishes at this point. And the other regime is a weak convergence to a centered normal distribution with some positive variance. Moreover, in this case, in the first case can be, we can always think to the case that x0 is equal to 0 because we can always consider a centered version of the random variables, and we can always reduce in some sense to this case. Now I give more precise definitions. The scalings are a family of positive numbers that goes to 0, but not so fast, because I have also this condition 1 are both. And for every choice of the scaling, we have a family of random variables, ZT, AT, that satisfies the large deviation principle with speed 1 over AT. So this goes to infinity. And the same rate function for every choice of the scaling, IMD, which is a quadratic function that uniquely vanishes at 0. Moreover, when we consider these two opposite cases, we recover the two extreme cases here. In fact, when AT is equal to this choice, we have a convergence to x naught, but in particular in this case, we have only this condition and this condition fails. And if AT is equal to 1, we have the weak convergence to the normal distribution. And in this case, this condition holds true and this one fails. Moreover, I can also say that the local behavior of the two rate functions for the moderate deviations and large deviations in the unique point where these two functions are equal to 0 is the same, because we have typically the second derivative is equal to 1 over sigma square, and sigma square is the variance of the normal distribution in the second regime. As a prototype example, I recall the case of this trivial case. I consider yt is a sequence of IID random variables. I introduce this symbol for the logarithm of the moment generating function, and assume that it is, these random variables are centered, and this means that they have expected value equal to 0. So we have the regime of the law of large numbers, and I have this ratio here, that satisfies the large deviation principle with linear speed, and the rate function is given by the Legendre transform of the function k defined here. And the other regime is the regime of central limit theorem. I have the square root and the denominator here, and it is well known that the limit is this normal distribution, and the family of random variables in this case is given by this expression, and I can check that I can recover with these two choices of AT, I can recover these two cases here. In this talk, I use the term non-central moderate deviations because I want to consider some cases in which we have a class of large deviation principles that fill the gap between a convergence to a constant and a weak convergence to a non-Gaussian, non-degenerating distribution. Some examples appear in these two papers. Essentially, are two papers. In the first one, the examples are one-dimensional. In this case, we have an example with multidimensional random variables, even if the weak convergence is trivial because the random variables are identically distributed. In our papers, in our results, we have this model, and there is this condition star that appears in our results. We have a compound fractional Poisson process. So we have the process of this kind. The sequence xn and the counting process are independent. Xn, the addenda here are random variable, are IID, and they are fine. The moment generating function is finite in a neighborhood of the origin. So I have a finite mean denoted by mu and a finite variance denoted by sigma square. I avoided the case that they are constant to avoid the trivialities. So this is positive. And this is a time fractional Poisson process with parameter nu in 0, 1. I recall the definition of time fractional Poisson process. I can see it as a time change version of a standard homogeneous Poisson process with intensity lambda. This is a inverse of a stable subordinator here, and it is independent of the external process here. It is the inverse of a stable subordinator. This means that it is defined in this way, where AT is a stable subordinator. And a stable subordinator, it is well known, it is a non-decreasing Hilbert process, such that the moment generating function of each random variable is defined in this way. So it is an Evitail case. And in fact, so we can say that the inverse does not increase too much. It is well known that the moment generating function of the random variable L nu t of the inverse of the stable subordinator can be expressed in this way, and it is finite for each theta, in terms of this function, which is the Mittag-Leffler function. It is easy to check that the moment generating function of the compound fractional process can be expressed in this way in terms of the function, the Mittag-Leffler function, and the moment generating function of the addenda of the sum, formula 2. Our results are these three propositions. The first one is LDP and LDP with convergence to 0 and with speed t equal to t, the suitable rate function, and for every mu, the mean of the random variables xn, we have that the convergence is to 0 and that function uniquely vanishes at 0. Moreover, we have proposition 2 with the convergence to a non-Gaussian distribution, and we have two different cases when mu is equal to 0 and mu is different from 0. And the proposition 3 gives the non-central moderate deviations. And again, we have this difference between mu equal to 0 and mu different from 0. I have to introduce this quantity here, defined by 3, and in the proof, I have to take into account the asymptotic behavior of the Mittag-Leffler function when the argument goes to plus infinity and to minus infinity. Formula 4. Proposition 1, under condition star, I can consider this function here, which is always non-negative, because here the difference is when the quantity here is negative, I have this condition and I have 0. And as we assume that this function is essentially smooth, so with we have the LDP for this ratio with this speed, and the rate function ILD is defined in this way as the Legendre transform of this function. Note that this function can be equal to infinity when this is equal to infinity. We have an application of the proof. We have to consider the function defined as a limit of these quantities. This part cancel. We take into account formula 2. And moreover, we get this limit here where lambda is as in the statement of the proposition by taking into account the asymptotic behavior of the Mittag-Leffler function. The case when the random variables are all equal to 1, we have the compound sum coincides with the counting process, and in such a case, we recover a result in another our previous paper. In that paper, the expression of the rate function is different, but one can check quite easily that the two rate functions are actually the same rate function. One can wonder what happens if nu is equal to 1. When nu is equal to 1, we have some problems because we can again recover, we can apply the Gartner-Ellis theorem, and we can obtain an analogous result. But in such a case, the rate function is equal to 0 only on a point which depends on mu. So we prefer to avoid this case to get some non-central moderate deviation result. So we are interested into this case. Proposition 2 provides the weak convergence results, and we have a difference for the case mu equal to 0 and mu different from 0. Again, we have to consider this condition here, and in this case, we have to consider the function, the value defined in equation 3, which depends on mu equal to 0 and mu different from 0, and we have this weak convergence in this case when mu is equal to 0 to a random variable of this kind. Here, Z is a standard normal distributed random variable independent of L mu 1. And when mu is different from 0, we have this, the weak convergence again of the same expression, but here the exponent changes and the limit is different. The results are known, but are known in the literature, but can be checked by consider the pointwise limit of the moment generating function. So we omit the details. Finally, the non-central moderate deviation results. Again, I consider condition 3. Again, I consider this quantity defined in equation 3. And I have to consider this family of random variables, which depends on the scaling AT that satisfies condition 1. So we have the LDP with speed 1 over AT, and the rate function IMD depends on mu. We have two cases, the cases in red for the case mu equal to 0, and the case in blue when mu is different from 0. This can be checked again with an application of the Deterministic theorem. Again, we have to consider the limit of the suitable scaled logarithm of moment generating functions. We have to consider again some easy computations. Moreover, we take into account the expression 2, which provides this moment generating functions in terms of the Mittag-Leffler function. And we have the two cases mu equal to 0, mu different from 0. In this case, we have to consider this expansion, and by taking into account the asymptotic behavior of the Mittag-Leffler function, we get this limit. And if I consider the hypothesis, the Legendre transform of this function gives the rate function in the statement of the proposition. When mu is different from 0, we have to consider this expansion. It is quite different from this one. Note that here mu was 0, so this part disappears. In this case, mu is different from 0, so this part remains. And we have similar limit and similar computations, but the limit is quite different. Okay, and again, under our hypothesis, this limit satisfies the hypothesis to apply the Deterministic theorem. And if I consider the Legendre transform of this limit, I get the rate function in the statement of the proposition. These are the references. This is the book of deviations as a reference on large deviations, and these are the other references cited in this talk. Thank you.
Okay, so thank you for the talk. Is there any question here or from home? No? No questions? Yeah, okay.
Okay, so a very quick question. So you were considering the compound process under the hypothesis that the random variables X are IID, independent and identically distributed. So what of these results can be extended to a case in which they are not IID?
But I guess that is one can consider some extensions. Probably an attempt that I could do is to consider cases in which their law are depends on the evolution of some ergodic Markov chains. One have to consider an ergodic Markov chains, for instance, with finite state space and ergodic, and the law of the jumps depends on the evolution of the Markov chain at each time. And under an hypothesis of this kind, I guess that one can obtain an extension of the result, the results presented here, even if I guess that the rate function are not so explicit also for the moderate deviations, because one, in this case, there are some expression in terms of some eigenvalues related to the asymptotic behavior of the underlying Markov chain in terms of the Perron-Frobenius theorem. Probably a result of this kind is possible, but it is not so explicit.
So if no other questions, no? Okay, so thank again.
Thank you.
And now we have a break for lunch, and then at 2 o'clock, so there is an open session, and then at 2:30 we have the first talk. Okay.